Hello, everyone, and welcome to this seminar. I am Zakia, and it's my pleasure to be the host of this seminar. So these seminars have been held for past couple of months, and we are hoping to keep them regularly going so that we can provide a space and time for the members of PermafrostNet to share their research. And I want you all to let me know if you are interested in presenting. We will be so happy to have you presenting your work here. And moving to the presentation, today we will listen to Adam Kirkwood talking about his work on permafrost and mercury, revisiting a global hazard assessment at the regional scale in the Hudson Bay Lowlands. Thank you so much, Adam, for accepting to present your work. Much appreciated. And let me begin with a brief introduction about you, and then we can listen to your presentation. So Adam is a PhD candidate at Carleton University. His PhD research is focused on the transition of permafrost zones from continuous to discontinuous in the Hudson Bay Lowlands. His research is exploring the concentration of mercury stored in permafrost, the potential for it to be methylated via soil microorganisms, and the transport of this mercury through degrading permafrost environment. His previous research has investigated the microbial mediation of greenhouse gases from thawing permafrost and the role of permafrost in influencing peat chemistry and microbial community. In addition to his research, Adam is passionate about northern research and enjoys field work and working with northern communities. And he is an active networker within the permafrost research community. Thank you again, Adam, for doing the presentation, for accepting to participate, and the floor is yours.
Awesome. Thank you very much for the introduction, Zakia. All right, so thank you very much, everyone, for coming to my presentation today. I'm excited to be able to talk to you all about my work taking place in the Hudson Bay Lowlands. And as introduced, I'll be talking about permafrost and mercury and revisiting a global hazard assessment, specifically with data from the Hudson Bay Lowlands. So to get started, I'll say that I've recently moved to Ottawa, which is on the unceded territory of the Anishinaabe Algonquin territory. And the work that I'll be presenting on today had field work from a few territories, namely the Mushkegowuk territory and the Wendat Traditional Territory, as well as Treaty 5 territory in northern Manitoba. And I'm very thankful, especially to community members from the Wendat Traditional Territory, for accepting me into their community and coming out onto the land with me, providing information on their traditional knowledge and allowing me to share some of my Western methodologies with them. I've really learned a lot from it and will carry that forward as a Northern researcher. So I won't spend much time on this because Zakia gave a very nice introduction, but for some of you who know me, you might be wondering why I'm a PhD candidate to geography now. At Carleton, I've recently transferred from Carleton University, and I'm still working with a really awesome supervisory team. So I'll get started by introducing mercury a little bit. And for those of you who aren't very familiar with it, it's a global pollutant and it's a heavy metal. So mercury can be transported to high latitudes up to the circumpolar north via atmospheric circulation. Mercury is released by both anthropogenic and by natural forces. So anthropogenically, it comes from things like cement production, from coal burning, gold smelting, but it also comes from natural sources, which is why we find it in deeper layers of the soil that kind of have been immune from anthropogenic emissions. So it comes from things like volcanoes or from forest fires. And because of atmospheric circulation, very commonly it ends up in the north. And as it's deposited from the atmosphere to the terrestrial environment, it'll be collected by foliage, by vegetation, by grasses, and it will eventually be incorporated into the soil layers. And because we're in the north, very often it will be assimilated into permafrost and it'll kind of be locked away, for lack of better terms. And so this is a diagram that was produced by Dastur et al. In 2022 as part of their report to the Atmospheric Mercury Assessment, Arctic Mercury Assessment Program. And you'll see I've outlined in the red box that they estimate that there's a significant amount of mercury stored in soils of the circumpolar north. And mercury is listed as a chemical of concern by the World Health Organization due to its potential impacts on human health. So because it's a known contaminant and it's known to potentially impact human health, there are many different guidelines on fish consumption for mercury, because fish with high levels of mercury could pose potential threats if too much is consumed. And this is because mercury has a very unique ability to transform from its inorganic form of regular inorganic mercury into its organic and neurotoxic form of methylmercury. So microbial communities can basically take this inorganic mercury, attach a methyl group to it, and turn it into methylmercury, which is better able to bioaccumulate and biomagnify up food chains. So it's also more highly mobile, so it'll work its way through ecosystems and often end up in aquatic systems. And because it's a biomagnifying species and a bioaccumulating species of mercury, that means that it can go from things like bacteria into algae, into small forage fish, and eventually into bigger fish. And it will keep all of the mercury going up the level. So eventually the predatory fish will have much higher concentrations of methylmercury. And so understanding mercury storage and mercury methylation in the Arctic is important because of the reliance of northern communities on country foods. And recently in the Arctic Mercury Assessment Program report, they've indicated that fish consumption is a potential route of exposure for mercury, and it could be hazardous in the future. And so several recent papers have estimated or discussed how much mercury is stored in the circumpolar north and in permafrost specifically. So there's this paper from 2018, which states that permafrost stores a globally significant amount of mercury. Another paper from 2020 that revised the 2018 estimate, and then a 2021 paper that estimated how much mercury is stored in permafrost of Siberia. And so these papers actually all have very different estimations of how much mercury is stored in the circumpolar north. So this first paper estimates that in the top 3 meters of the soil profile in the circumpolar north, there's about 1,656 gigagrams of mercury. And for reference, a gigagram is 1 million kilograms. Later in 2020, Lim et al. Decided to revisit this estimation and said that in the top 3 meters, there's actually only 597 gigagrams of mercury. So this is quite the discrepancy between the previous estimate. Then in 2021, this paper by Rutkowski et al. That was looking at specifically eudoma deposits in Siberia estimated that just in Siberia alone, there's 542 gigagrams of mercury, not including the rest of the circumpolar north. So there's some very different estimates that are going on in terms of how much mercury is stored in the circumpolar north. And so all of these estimates are made with a ratio between carbon and mercury. So it's called the ratio of mercury to carbon. And this ratio is important because permafrost carbon has kind of been a buzzword, and there's been lots of research going on to this in the last 10, 15 years. So there's lots of very well-developed maps of how much carbon is stored in soils of the circumpolar north and how much carbon is stored in permafrost soils. And so by understanding how much mercury is stored per volume or per mass of carbon, researchers can take this ratio and apply it to mapped carbon stores to have an estimation of mercury storage. And that's exactly what the Schuster et al. 2020 paper, 2018 paper, and the Lim et al. 2020 paper did. They took carbon maps like this one from Hugelius et al. 2014, applied their ratio, and developed their own map of mercury storage. And that's why this carbon map and this mercury map look very similar. So the goal of the work that I'm presenting on today is to assess how much mercury is stored in the Hudson Bay Lowlands. So we're doing this using region-wide field data to kind of calibrate this global model to see how well it fits for the Hudson Bay Lowlands. But then I also wanted to determine the importance of spatial variation during this upscaling process, because both the Schuster et al. 2018 paper and the Lim 2020 paper just took a single ratio and applied it to the full circumpolar north. So I was curious to understand how spatial variation impacts how much mercury will be estimated. So I'll get started by introducing my study region, which is the Hudson Bay Lowlands, and it's the largest peatland in North America. So you can see its outline in this area black here, following the coast of Hudson Bay. Oops. So this area has previously been estimated to store 30 petagrams of carbon, where a petagram is 1 billion kilograms. So there's a very large storage of carbon in this area, and it has an area of 372,000 kilometers squared, where it's nearly continuous peatland. And to put into perspective how big that is, the country of Norway is 200 kilometers squared. So this is a large peatland, almost the size of an entire Nordic country. The Hudson Bay Lowlands is also a very unique environment, which is why myself and others are very interested in it. I said it's the largest peatland in North America, and it's also the second largest northern peatland in the whole world. This area has an emerging coastline. It has very rapid isostatic rebounds. It's at about a rate of 1 centimeter per year, which is among the fastest globally. And it's also an anomalously cold area. So you'll see that this dot in blue just popped up on the map. This is the climate station at Churchill, Manitoba. So in Churchill, it's at 58.7 degrees north. And the Environment Canada climate normals show that the mean annual air temperature here is about minus 6.5 degrees Celsius per year. To put that into perspective, Whitehorse is at a similar, a little bit higher latitude at 60.7 degrees north. And Environment Canada climate normals show that here the mean annual air temperature is only minus 0.1 degrees Celsius. To put it into context a little further, Oslo, Norway, which is at 59.9 degrees north, is at about 7 degrees Celsius. So this area is very anomalously cold, and we can see that's reflected by it having North America's lowest latitude continuous permafrost. You see that zone of continuous permafrost following the coast of Hudson Bay. So coming back to the Schuster et al. 2018 paper, they estimate that there's a very large stock of mercury in the Hudson Bay Lowlands. So you can see I've outlined the Hudson Bay area in black on both of these boxes. And in each case, from 0 to 100 centimeters and 0 to 300 centimeters, the Hudson Bay Lowlands has about the highest concentration in all of the circumpolar north. So that brings me to some of the questions of my research. So first, I wanted to just have a general estimation of how much mercury is stored in the Hudson Bay Lowlands based on a single region-wide average. So taking all of the samples from across the region and taking one value and applying it to all of it to see how much mercury we estimate. So to do this, we compiled a data set of peat cores from 39 sites across Northern Ontario and Manitoba. So on the right, we have a land cover map of Ontario, and each of these black dots is a sampling location. And then we took all of these samples. So from the 39 sites, we have a total of 50 cores. And when we broke that down into subsamples, we had over 900 subsamples. And all of these subsamples were measured for their total mercury concentrations using this machine here, which is a direct mercury analyzer, which measures the total amount of mercury that's there, both the organic and the inorganic species. We also measured elemental composition, specifically interested in carbon content, using an Elementar isotope cube. So once we had all of the data, we started doing just some general calculations to understand how much carbon is stored in the region and how much mercury is stored in the region. So these are very basic equations that are used to map or calculate how much carbon is stored within a peat core. So we took the mean carbon content of all of the samples, or sorry, of the sample for a core, multiplied it by the mean bulk density for the core, and then multiplied it by the depth of the core. And this gives us an estimation of how much carbon is stored in that core of peat that we collected. So after doing this for all 50 cores that we collected, we find that the mean areal carbon storage for peat cores of the Hudson Bay Lowlands is about 78.5 kilograms of carbon per meter squared. Now we can do the exact same calculation again, but this time we just replace carbon with the mercury concentration. So multiplying the mean mercury concentration of the core by the bulk density of the core and the sample depth. So after doing this for all 50 cores and taking an average of all 50 cores, we find that the mean is about 9.23 milligrams of mercury per meter squared. So using this data on the mean areal storage values for carbon and mercury, we can actually use that to extrapolate it to the larger area of the Hudson Bay Lowlands. And we did this following the methods of Packalen et al. 2014, who did the original carbon estimate for the Hudson Bay Lowlands. So because we already know the mean areal carbon storage, we can essentially apply that to the surface area of the peatland. So we know that the Hudson Bay Lowlands area is 372,000 kilometers squared, and that 90% of that area is continuous peatland, so 342,000 kilometers squared. So to calculate carbon storage, or to do a broad estimation of carbon storage for the region, all we have to do is apply that mean areal carbon storage to the area of peatland. And we find a revised estimate of about 27.3 petagrams of carbon. So this fits fairly well with the data from Packalen et al. 2014, who estimated about 30 petagrams. Now we can do the exact same calculation again, but this time replacing carbon with mercury. And the first estimation we have of how much mercury is stored in the Hudson Bay Lowlands is about 3.08 gigagrams based on region-wide field data, applying a single value to the whole region. So that brings me to my second question of how does including within region spatial variation affect the accuracy of the estimation? Is it going to significantly change how much mercury we estimate in the region? So what we find is that total carbon and mercury stored in the cores specifically is significantly different between environments. So we sampled fens, bogs, pulses, and peat plateaus, as well as adjacent thermokarst fens. And so for all of the cores, we find fairly different values of mean total mercury and mean carbon. So for fens, we find about 9 milligrams of mercury per meter squared, and then the carbon mass is a little bit lower at 83.61 kilograms per meter squared. For bogs is the highest category of both total mercury and of carbon. We find that there's 10.86 milligrams of mercury per meter squared on average in bog samples, and about 114.3 kilograms of carbon per meter squared. Now, Paul says it's a little bit lower on both fronts, and this is likely because the peat deposits aren't as deep because they're typically closer to the coast of Hudson Bay and haven't had as much time to develop. So the mean total mercury is about 8.61 milligrams per meter squared, and carbon is a little bit lower at 36.3 kilograms per meter squared. And this is the likely reason that our estimate of total or carbon storage in the region is a little bit lower than 30 petagrams estimated by Packalen et al. So using land cover data set, we assessed the coverage of the proportion of each of these landscape types, being pulses, fens, and bogs. So just a quick note on this section is I'm currently limited by the land cover data that's available for the region. So there are no land cover data sets that assess the area of pulsa or peat plateau or thermokarst fen. They're either classified as fen or bog or treat areas based on their surface vegetation. So at this point, I'm not able to look at specifically the area of permafrost feature and parse out how much mercury is stored in permafrost versus unfrozen fens and bogs. That being said, I have mostly focused on fens and bogs for this part of the analysis. So we find that of the Hudson Bay Lowlands, about 32.2% of it is covered by fens, which translates to about 120,000 kilometers squared. For bogs, they cover about 38.7% of the landscape, which is about 144,000 kilometers squared. Now, because we don't have that good land cover data set, I had to group the rest into other, either because it's not classified on the land cover data set, for example, the pulses and the peat plateaus or thermokarst fens, or also because there's forested areas in the south or tidal areas along the coast that we don't have data for. So we grouped this into an other classification, and we applied the mean value of mercury storage to that other category. And this is something that we're working on improving in the future. So when we segment it into dominant lands classes by the region, I just do the exact same calculations that I showed on the previous slide. So applying the average mercury storage and then multiplying it by the area. So for the other category, we find that there's about 1 gigagram of mercury. In fens, it's a little bit higher at about 1.08 gigagrams. And in bogs, it's again a little bit higher at 1.56 gigagrams. So to determine how much is in the full region, all we do is have to sum this up, and the cumulative mercury storage is about 3.64 gigagrams. And this is compared to the 3.08 gigagrams we got from applying that blanket estimate where we just used that one mean value. So what this shows is that in this region, which is a ubiquitous peatland, a very homogeneous, continuous peatland, accounting for spatial variation only leads to marginal improvements in estimating how much mercury is stored here. But that also leaves another question, is that so far, these calculations haven't explicitly accounted for peat depth. They've done so in a marginal way because they have an average of, or from peat cores of many different depths, but it doesn't explicitly say for this area that has 300 centimeters of peat versus this area that only has 50 centimeters of peat. So what happens to our estimate of mercury storage when we include that? So this is a map of peat depth that was modeled by Hugelius et al. In 2020 to produce their estimate of how deep the peat is. And they did this for the full circumpolar north. And in this map, I just trimmed it specifically into the Hudson Bay Lowlands. So we can use this data to account for the spatial variability of peat depth. But before we did this, I wanted to do a quick quality check to see how well it compared to measured peat depths in the Hudson Bay Lowlands. So all of these purple dots you see on the map is an area where someone has either drilled or probed or dug to measure peat depth in the region. So we compared it to the modeled peat depth to see how comfortable we would be in using this data set to upscale to include peat depth in mercury calculations. And so what we find is that the modeled data actually fits fairly well with our measured data. So the modeled data is on the y-axis and the measured peat depth is on the x-axis. And it has a correlation value of 0.7, and it's very highly significant. So I feel fairly comfortable using this for now, but working on an updated peat depth map is something that I'm currently working on. So we find that the mean peat depth of the model data is 177 centimeters in the region, and the mean measured peat depth is 184. So it fits well enough that we feel comfortable using it. So to calculate mercury storage accounting for peat depth using this data, because it's a raster data set, we did all of the calculations on a per cell basis. So for each of these cells of estimated peat depth, we calculated the volume of peat per grid cell. So the grid cells are 10 kilometers by 10 kilometers. So we just multiplied the area by the peat depth to get a volume of peat per cell. Once we had the volume of peat per cell, we just multiplied the volume of peat by the mean density of mercury. So being how much mercury in milligrams per meter cubed, and that gave us mercury storage per cell. And then we summed all of the cells to get a cumulative value. So once we summed all of the cells, we found that including peat depth revised the estimate to about 3.49 gigagrams of mercury. So keep in mind, this didn't include fens versus bogs. This is just another blanket estimate, but this time including peat depth as the spatial variant. And so again, this is compared to 3.08 gigagrams. So including peat depth didn't drastically change how much mercury we calculated to be stored, which to me was a bit surprising. I expected that when we explicitly accounted for peat depth, it would either significantly increase or decrease the amount of mercury, but that's not the case, which is something that I find interesting. So moving on to the next question and kind of coming back to my introduction where I was talking about those papers that were modeling mercury storage based on this mercury to carbon ratio. So how well does this region or a region-specific ratio of mercury to carbon estimate mercury storage? So again, it's a very similar calculation to before, and I want you to recall that we estimate that there's about 27.3 petagrams of carbon. So to use a ratio of mercury to carbon, we just take the mean ratio of mercury to carbon that can be converted to gigagrams of mercury per petagram of carbon, and then multiply it by our carbon storage. So it's a very straightforward calculation. So we find a mean ratio of mercury to carbon of 0.12 gigagrams of mercury per petagram of carbon. And we multiply that by our estimated carbon storage of 27 petagrams. It estimates that there's about 3.27 gigagrams of mercury. Again, fairly similar to our original calculated value of 3.08 gigagrams. So of course, this site-specific ratio applied to site-specific carbon measurements is going to yield good results. So what I was curious about is if we take carbon content estimations from elsewhere, someone who didn't do it specifically for the Hudson Bay Lowlands, and apply our ratio to those carbon maps, similar to the way Schuster et al. 2018 did it, how well does that data fit to our analytically measured and calculated mercury storage? So again, we have our mean ratio of mercury to carbon of 0.12 milligrams of mercury per kilogram of carbon, which is scales with gigagrams per petagram. So if we're looking at the Hugelius carbon map from 2013, where we're looking at the top 1 meter in the Hudson Bay Lowlands, there's between 25 to 50 kilograms in some spaces, which would, with our ratio of carbon, indicate that there's about 3 to 6 milligrams of mercury per meter squared. Or if we apply it to the 50 to 100 kilograms that they estimate, that would say that there's about 6 to 12 milligrams of mercury per meter squared. And this is compared to our actual mean storage of about 9.23 milligrams. So if we take the mercury to carbon ratio that we derived in our region and applied it to carbon values that weren't specifically developed in our region, it actually still fits well. So now I'm going to pose the opposite question. So if we take a mercury to carbon ratio derived from elsewhere and apply it to our region, what's going to happen? So I'm going to do that with these two papers that I introduced at the beginning, the Schuster et al. 2018 paper and the Lim et al. 2020 paper. So both of these papers estimated how much mercury is stored in the full circumpolar north, but neither of them have samples from the Hudson Bay Lowlands. So this is the map of samples that Lim et al. 2020 used for their circumpolar estimation. They have 6 cores from northeastern Russia, and they find a mean mercury to carbon ratio of 0.19 gigagrams of mercury per petagram of carbon. This is a map of the samples that Schuster et al. 2018 used. You can see that their data set is more robust, but again, no samples from the Hudson Bay Lowlands, and only a comparatively small amount of samples from permafrost regions compared to samples from this latitudinal and longitudinal gradient of the United States and Canada. And so for their mean ratio of mercury to carbon, they find about 1.6 gigagrams of mercury per petagram of carbon. So if we apply these ratios to our carbon storage from the Hudson Bay Lowlands, how much mercury are they going to estimate? So just a quick reminder, in our study, we found 0.12. If we multiply that by our 27 petagrams of carbon, we estimate 3.28 gigagrams of mercury. If we take LimAL 2020's value of 0.19 gigagrams of mercury per petagram, apply that to our calculated carbon storage, they would estimate 5.19 gigagrams of mercury. So it's a little bit higher than any of the estimations that we have done. If we move on to the Schuster et al. 2018 paper that estimates 1.6 gigagrams of mercury per petagram of carbon and apply that to our 27.3 petagrams of carbon, this paper would estimate that there's 43.7 gigagrams of mercury in the Hudson Bay Lowlands, which is significantly higher than any estimation that we've made. So by comparing our data based on field data and samples, it would decrease this global hazard estimation by over 10 times in this region, which is a very significant decrease, especially for a heavy metal contaminant. And then I also want to just take a minute to point out that this 5.19 gigagrams of mercury that we would get from this estimation, it is statistically closer to the 3.28 gigagrams of mercury that we estimate based on region-specific data. But when we're talking about 2 million kilograms of a toxic heavy metal, it's a very significant difference to the communities that live in these regions. So this is just to demonstrate the importance of using local field data in the region compared to pulling in data from outside. So to start wrapping up, I'll talk about why this matters and how it relates to permafrost hazards. I've talked a lot about mercury and carbon and bogs and fens and only mentioned permafrost a few times. So you're probably wondering what angle I'm approaching this from. So I am part of theme 4 and 5 in PermafrostNet. And for those of you who aren't familiar with the structure, theme 4 is the hazards associated with permafrost thaw. So at a theme 4 meeting that we had in December 2021, we started brainstorming how people are defining permafrost hazards. And so we had a really good discussion. It lasted longer than the meeting was supposed to, but it was perfect because it kind of really transformed the way I was thinking about permafrost hazards. And I think it did the same thing for some of the other people at that meeting. And so, of course, the first thought of permafrost hazards that came up was damaged infrastructure. This seems like the logical one. I think it's probably safe to say that this is the hazard that most people think about associated with permafrost thaw. It can damage the roads, the railways, the runways, the infrastructure that's built on top of it when it starts to thaw. But then we started thinking about other things. And one of the things that came up was changes to the health of aquatic ecosystems and contaminant cycling. Changes in travel routes and traditional territories also came up. We've heard this from northern community members who've said that as the permafrost thaws, it changes traditional travel routes. People have to take other routes and it can become more hazardous. And then also the impact that permafrost thaw has on food security. So kind of where I come into this is these two potential hazards that are outlined in red, the changes to the health of aquatic ecosystem and contaminant cycling and the impacts on food security, because these are cumulative effects. So as the permafrost thaws, it can start mobilizing mercury. Mercury can be methylated and it's find its way into food chains, which can have impacts on food security. And so looking at chapter 2 of my thesis, which I'm not going to talk about too much other than to just give you an idea of how this work all relates to each other, is I'm focusing on how, as permafrost thaws, how it releases mercury from raised and dry environments and frozen environments, like from a pulsar or a peat plateau, to a subsided and saturated environment like a thermokarst fen. And so once I'm able to understand how much mercury was in the permafrost and then understanding how much permafrost is thawed, we can look at how much mercury is going into these different environments. So chapter 2 is looking at how these different environments are able to produce methylmercury. So specifically the microbial communities, the biogeochemistry, the temperature, the vegetation, how all of these things impact this production of methylmercury, which is the organic and neurotoxic form of mercury. So to finish up and to start recapping, the main takeaway points of the work that I'm doing is that mercury storage in the Hudson Bay Lowlands is significantly lower than what a very highly referenced global estimate says. The Schuster et al. 2018 paper I checked last night has been cited in peer review literature 264 times, and this isn't including the mercury, the media attention that it's gotten, or the times that it's been presented at conferences or in seminars. And so in the Hudson Bay Lowlands specifically, including spatial variation only led to marginal improvements in mercury storage. And I think this is a case that's very specific to the Hudson Bay Lowlands because it's this giant, almost single terrain unit or landscape class of peatland. And so applying a single value to an area that's very ubiquitous or homogeneous works well in this case, but likely wouldn't work as well in other environments that are more heterogeneous, where there's different superficial geology deposits kind of all over the place with interspersed peatlands and ponds. It would be a very different analysis in an environment outside of the Hudson Bay Lowlands. And then second, this ratio of mercury to carbon does have the potential to work well if it's derived within that environment. So for example, the data I presented on today showed that these ratios of mercury to carbon do a good job in estimating how much mercury is stored in the region. But I wouldn't feel comfortable taking my mean ratio of mercury to carbon and applying it to a peatland in, say, the Old Crow Flats or the Mackenzie Delta, because it probably won't work as well. And so with that, that's all I have for today. I thank you for coming to listen, and I'm happy to, I think we have quite a bit of time for any discussion or questions, and I'm happy to hear from you.
Thank you, Adam, for your presentation. That was a great work and very, very nice presentation. So as you said, if anyone has a question, please just unmute yourself and ask your question.
Hi, Adam. A couple of thoughts if I can just ask them. First of all, thanks for a really good presentation, very clear. So what I understand was that you were focusing on total mercury storage in today's presentation. And one of the things you showed was that actually the amount of total mercury stored in the pulsars, which are the frozen parts of the landscape, was actually less than the amount per square meter than the amount that's in the bogs and the fens. So can you explain to me a little better about what I think is going on is that when you thaw those permafrost landforms, you actually create the methylmercury, which is the most worrisome element. Is that right? Because logically, otherwise, they're the least important parts of the landscape, and the bogs and the fens already have, presumably, some mercury in them that actually came from thawed pulsars, which were frozen at some time in the past, say, during the Little Ice Age. Can you just comment a little bit on that? Because it sounds like, hey, it's a dilution that's taking place rather than a concentration when you thaw those parts of the landscape.
Yeah, for sure. So we do have data on methylmercury between active layer environments, top of permafrost, thermokarst. And what we find when we're comparing thermokarst fens to just unfrozen fens from lower latitudes is that typically there is more methylmercury in concentration and volume, but also in terms of the proportion of methylmercury compared to total mercury. So basically when we're looking at it as a percent methylmercury, thermokarst fens typically have higher percent methylmercury, which indicates that these environments are more able to produce methylmercury. And so in terms of your question about dilution versus concentration, it's not so much the concentration that matters. It's the ability of these environments to produce methylmercury. So that's something we're still looking into in my other chapter, is looking at the different vegetation composition, microbial composition, and how when it goes from this frozen environment where there's not much microbial activity to this thawed environment where there's a much higher abundance of nutrients and microbial activity in warmer temperatures, it's more likely to produce methylmercury.
Okay, thanks. And just perhaps one other comment. You were saying, you were kind of surprised that when you started using the spatial differentiation, you didn't get much of a change. So in my head, I went, that's because your sampling scheme was very good to begin with, right?
Yeah.
Basically, what that means is you actually had a pretty good, in all your samples, you had a good representation of the population, even though you didn't know necessarily that you did have. And also you had 900, I think 900 samples, something like that. That's an awful lot. So it's not really too surprising that you converged in all of those samples on quite close to what was the population mean, which is why when you multiply everything out, it doesn't change too much. So congratulations on good sampling.
Thank you.
Thanks.
Hi, Adam. This is Stefan, and we're 5 people here watching you on a big screen, but we don't have a camera.
Oh, wow.
Thank you for walking us through all this in such a nice story. I'm just wondering, you have a phrase that says only a marginal improvement, and I'm wondering, do you know that it's an improvement, or are you actually saying it's a marginal difference to a method that you know is better?
It's kind of hard to determine which method is better. If I were, to kind of have to pick which method I think would be most representative, it would definitely be the one that includes spatial variation. Because even though there's small differences, the reason I think there's small differences is only because this environment is very continuous and ubiquitous. So there are very different areas of fen and peat, fen and bog, but in another environment where kind of the environment is more different from each other, then I think including spatial variation would definitely be more important. So it's hard to say which is better, but I would likely assume that the one that includes the spatial variation would be a more representative estimate of how much mercury is in the region.
Hey, Adam, that was really great. I'm super interested in all of your work since, you, Charlotte, and I are all taking these approaches in different circumpolar regions. And I think we're coming up with some pretty similar findings, although, the exact differences amongst the regions are fascinating. So I really liked seeing your presentation, and I'm excited to see your other chapters as well. So we could talk for a long time, but I did want to say, I'm seeing really similar results as you did regarding that, bring a lot of that, those issues with the Schuster product. So I know obviously HBl has tons of carbon in it. Did you end up getting to the mineral? Did you see a really, really distinct difference between the mineral and carbon? Because I know that's kind of been a constant throughout these different regions.
Yeah, that's a really good question. It's actually something I didn't get to in the presentation. And that's one of the limitations of this approach, is it is specifically suited to peatlands. Like, I don't think using the ratio of mercury to carbon works well in mineral samples. And that is part of the reason why the Schuster paper has such a high estimate of mercury to carbon ratio, because there's so little carbon in the sample that it's saying there's no carbon, but there's so much mercury that it's really inflating the ratio. And I think that's the same thing that happened in the Rutkowski paper from Siberia, because it's predominantly organic rich mineral samples. But it's more to do with like grain size or saturation or things that determine how much mercury would be in the mineral. So that's kind of one of the caveats of this work, and we're preparing it for publication. And I think we have to say, like, this works for a peatland, but there's the other approaches taken for mapping mercury and mineral deposits.
Cool. And I'm just super curious, what are your fens and bogs like? I know you don't have to give me a huge like spiel about it, but I'm just curious about like how productive are those fens? Like how much of that really rich vegetation is in them? Just so I can think about a difference between my sites in the Taiga Plains.
So I haven't been to the southern fens myself. Those were data sets that I compiled from one of my colleagues. Along the Hudson Bay Railway in northern Manitoba and in northern Ontario, like they're very sedge dominated fens.
I want to thank you, Adam, again for presenting. That was such a great work. And I learned a lot, and you explained it very clearly. I really liked the presentation. Okay, so thank you everyone for joining us, and have a nice rest of the day.
Yes, thanks for coming, everyone.